In this section, we will explore the probability axioms, and we will talk in one example about the expected value. Okay, so what is the probability axiom? So let's read the first definition or the first theorem or axiom. It says let S be a sample space. So basically think of S being the universe. So when I'm flipping a coin, the universe is either heads or tails. So that would be called the sample space. Getting heads or getting tails would be the event. Okay. Now the probability function P from the set of all events S to the set of real numbers satisfies the following three axioms. So basically this is saying that, if you think of the probability as being a function, that function satisfies these following three. For any event A and B that are in S, so if you have A and B events in S, for example, the tails or the heads, they're events in the sample space, then the probability of any event will either be 0 or 1 or something in between. So basically you cannot have negative probabilities. The probabilities have to be 0 or have to be 1. Okay, the probability would be 0 if the event is impossible to happen, and the probability is 1 if the event always happens. Okay, now the probability of the empty set is basically 0, and the probability of the universe is 1. Okay, so the probability that the universe is going to happen, so in other terms, the probability that I land heads or tails is guaranteed. It's got to be 1. There's no way on earth I can get anything else when I flip a coin. And the probability of the empty set, this is the set with nothing, is basically 0. And I also know that if two sets are disjoint, so if they have nothing in common, then the probability of the union of the two of them is the probability of each one of them individually. So what does that mean? Suppose that one set had probability, or one event had probability of 0.8, and let's say the other event had a probability of 0.7. When I add 0.8 plus 0.7, I get 1.5. So that automatically tells me that these two events, A and B, have some kind of overlap. For some reason, they're not separated. They share something in common, okay? So that's how I can use this to my advantage. Now, suppose that A is an event in a sample space, and they want us to deduce that the probability of A complement is 1 minus B of A. So let's go ahead and take a look at a proof here. This is a short proof. I'm going to say, let A be an event in the sample space. And the sample space is called S. So automatically, the A complement, also known as A complement, aka A complement, and A have nothing in common. Then A complement and A share nothing. Okay, how do I know this? Well, I know this from theorem 6.2, right? There was a theorem, a table that said something like this. A complement intersected with A is basically the empty set. Also, A complement, and I know that A complement union the A is basically the whole universe. Okay, so this was basically theorem 6.2 point something. It was called the complement law. It was that table with all the different theorems. Now, I care about one of these. Specifically, I care about this one. And I also need to know that A and A complement are not overlapping. They're disjoint. So the first one tells me that the two sets are disjoint. So disjoint. This means that A and A complement are disjoint. Okay. And so since A and A complement are disjoint, then I will know the following. I will know that if they are disjoint, their intersection is empty. That means that the probability of A complement union A is the same thing as the probability of A complement plus the probability of A itself. Okay, how do I know that? I know that because of this. It's one of the axioms. The probability of A union B, when A and B are, disjoint, is the probability of the first one plus the probability of the second one. Now, what is A complement union A? This is the whole universe. So P of S is equal to P of A complement plus the probability of A itself. Okay, so again, A union A complement is the same thing as the whole universe because of the complement law. That was theorem 6.2.5, I believe. But I know that the probability of the universe is equal to 1. That's because of the second axiom in my table above. So that could be replaced with 1. The whole thing here can be replaced with 1. And that's the probability of A complement plus the probability of A itself. And they want me to isolate the P of A complement. So I'm just going to move the P of A to the other side. And I'll end up with 1 minus P of A equals to P of A complement. Okay. In other terms, i.e., in other terms, the P of the complement of an event is the probability of 1 minus the, it's the 1 minus the probability of the event itself. So the probability of the complement of an event is 1 minus the probability of the event itself. So if you think about the sample space, which was heads or tails, if I knew that the probability of heads is 0.5, can I know the probability of tails? Well, the probability of tails is 1 minus the probability of not tails, tails complement. So in other terms, this is 1 minus the probability of heads. If you don't get tails, that means you got heads. And so that's 1 minus 0.5, which is 0.5 at the end. So that's how I could use this axiom, basically. Now, this is a silly example. We all know that the probability of heads and tails is 0.5, but that's just a quick, toy example to illustrate what this theorem is basically telling me.